Alrighty, tonight we're going to be talking about isotopes. So the question is, what are isotopes? And we kind of talked about this yesterday when we were talking about protons, neutrons, and electrons, but I want to really delve into it today. So different atoms of the same element can actually have different numbers of neutrons. And when this occurs, these atoms are called isotopes. These isotopes can occur both naturally or they can be man-made, and they play a large part in determining the atomic mass of the element, and we'll get into that in the next slide. But first of all, I wanted to talk about some examples of isotopes that you would have encountered in your real life and maybe not in your real life. So carbon has different isotopes. We have carbon-12, which when carbon whose atomic number is 6, means it has 6 protons. So carbon-12 would have 6 neutrons. Carbon-13 has 7 neutrons, and carbon-14 has 8 neutrons. So you can see that we increase in the number of neutrons each by 1, designated by carbon-12, 13, or 14. When we're talking about isotopes, you must discuss the actual mass number so that you can determine, and you have to label them and call them by their mass number so that you can determine the number of the number of neutrons. Potassium has many different isotopes. It has potassium-39, potassium-40, and potassium-41. With potassium's atomic number being 19, that would mean that potassium-39 has 20 neutrons, potassium-40 has 21, and potassium-41 has 22 neutrons. Uranium, something that you may not have actually encountered in your real life, also has isotopes. Uranium-234, 235, and 238. And with 92 protons, that means that uranium-234 has 142 neutrons, uranium-235 has 143 neutrons, and uranium-238 has 146 neutrons. There's another element that has multiple numbers of protons and neutrons, and it is something that you encounter in your everyday life. It is the only one whose different isotopes actually have different names, or the most common one whose different isotopes have different names, and that would be hydrogen. Its most common isotope would be hydrogen. We also have deuterium and tritium. And here, hydrogen is H11, is how we denote it, and that means that it has 1 proton. So remember the number on the bottom here, that's the number of protons, the number or the atomic number, and the number up top here is the mass number, or the number of protons and neutrons. So hydrogen just has 1 proton. It has actually 0 neutrons. When we add a neutron, we get deuterium, and our denotation becomes 1, 2. So there's that additional neutron, or that first neutron, and then tritium has 2 neutrons, so it becomes H3 or H31. Now, isotopes can be stable or unstable, and that means that they are radioactive or not radioactive. So if the isotope is stable, it is considered not radioactive, meaning that it's stable as it is, it doesn't need to decay in order to become stable. If, however, it is unstable, it is a radioactive isotope. And 3 of these have radioactive isotopes. Carbon's radioactive isotope would be carbon-14, which is used in carbon dating. Potassium's radioactive isotope is potassium-40. So indeed, if you actually eat a lot of bananas, which are high in potassium, you ingest more naturally occurring radioactivity than most other people. And then uranium's radioactive isotopes are actually all 3 of them, U-234, 235, and 238. So that is something to keep in mind, though. Isotopes doesn't necessarily mean they're all radioactive. It just so happens for uranium that they are. But many isotopes, especially naturally occurring isotopes, can be stable. Naturally occurring isotopes can also be radioactive, though. Potassium-40 is a naturally occurring isotope, which is radioactive, but not harmful, nothing above background radiation that you experience in the world. Sorry, guys. So we talked about atomic mass and that isotopes directly affect this. And this is because atomic mass is the weighted average mass of all isotopes of an element. So we talked yesterday that it was the weighted mass of all atoms of an element. What I really meant was that it's the weighted mass of all the different isotopes that you can find in an element. And since atomic mass is made up of the number of protons and neutrons, the atomic mass of an element is primarily, the mass part is made up of protons and neutrons because electrons are so small. When you have a different isotope with a different number of neutrons, it has a different atomic, or a different weight. And so when we get the atomic mass of an element, we take the average of all those different atomic masses. And we can use this, we use an equation to do this. We say that atomic mass is equal to the percent of isotope 1 times the mass of isotope 1 plus the percent of isotope 2 times the mass of isotope 2, and so on and so on. And we do this because you want the weight, it's a weighted average. This word weighted right here means that it is the more an isotope is occurring, the more it's going to affect the atomic mass. So, for example, with U-235 and U-238, U-238 is primarily the most predominant isotope. It's like 90, yeah, it's somewhere around 99% predominant, and U-235 is only like 0.3% predominant. And so U-238 makes up the majority of its atomic mass, which is why it's higher than U-235. So, and this is important and can help you actually to figure out which of the isotopes is more abundant based on if you are given two different numbers of isotopes, and if the atomic mass is closer to one isotope than the other, then you know which one is more abundant. So let's look at an example. So chlorine 35 has an atomic mass of 34.968852 AMU, or atomic mass units, and is 75.77% abundant, so it's the most abundant one of the isotopes. Chlorine 37 has an atomic mass of 36.965303 AMU, or atomic mass units, and is 24.23% abundant. So in order to determine the atomic mass of chlorine, we would take 34.968852 AMUs and multiply it by 0.7577. So we take the percentage and we convert it into a decimal, and we'd add that to the second isotope, the isotope of chlorine 37. And our atomic mass is 35.45 AMU, or atomic mass units. And this makes sense because the atomic mass of chlorine 35 at 34.9 is much more predominant than, is much more abundant, than the chlorine 37, which has a higher AMU. So you would expect that this AMU falls closer to 34.96 than it does to 36.97, or 96, So the AMU leans heavier to chlorine 35 than 37 because it's so much more abundant. And that's really all you're going to learn about isotopes today. We're going to work on a worksheet on Monday where you're going to be calculating atomic masses and trying to figure out different isotopes and learn different things about different isotopes. So I hope you have a wonderful weekend, and I will see you on Monday.